This fourth video regarding rocket propulsion design equations will focus on derivation of the thrust equation. Additionally, we'll provide a brief overview of rocket developments as they pertain to human spaceflight. Our goal is going to be to take the rocket thrust equation and look at the two major cases that apply to thrust for a rocket. One will be at sea level, and the second will be at vacuum. So for any given rocket engine, we expect to get more thrust in a vacuum than we do at sea level. Robert H. Goddard provided significant accomplishments in the area of rocket research from 1912 to 1938. A few of these include U.S. patents issued for multi-stage rockets and de-Laval nozzles. Additionally, he built a vacuum chamber where he was the first to measure for identical rockets ambient vacuum thrust versus ambient 1 atmosphere thrust, where he showed the vacuum thrust would be actually larger. He also increased rocket engine efficiency from 2% to 64.5% by using a de-Laval nozzle, which he documented in the Smithsonian Journal, A Method of Reaching Extreme Altitudes in 1920. He was also the first to develop and launch the first liquid rocket, first scientific payload, and the first one to use rotatable carbon vanes in the rocket motor to provide thrust vector control or a steering mechanism for a rocket. He later incorporated a gyroscope sensor feedback for the control loop to actually help steer the vanes and keep the rocket going straight during its ascent. And later, in 1938, he was the first to develop centrifugal pumps suitable for use with cryogenic liquid fuels and oxidizers to allow for increased mass flow rates and also to increase the combustion chamber pressures as a ground-based proof of principle test. Goddard's multi-stage rocket patent is shown here. The first stage shows his typical converging diverging nozzle. There's a fuse leading to fuel discs, and when the last disc is spent here, a second fuse is lit that actually would light this second stage. Now at this point we'd have a separation plane, and this first stage would actually fall away, which would reduce his overall structural mass and allow the payload sitting on top of the second stage to be taken to a higher altitude. Now his scientific payload is shown on the left. He's got a barometer and a camera application shown here. You can also see that up in the upper stage, this area where there's detail shown here, he'd have a fuse section that would actually go up into this structure, burn out, and then a small charge would actually separate the scientific payload from the actual second stage as well. Goddard also briefly describes the use of his converging diverging nozzle and how it converts thermal to kinetic energy as shown here. Goddard chose to file U.S. patents in lieu of journal publications to document his research. During the early period of Goddard's research, especially around 1914, there are no technical journals that will accept rocket-type technology or research efforts. So he was initially wise to use U.S. patents to document his ideas. And what he's doing is he's attacking the what he thinks are serious problems with rocketry. One is, if you see here, he's got his de-Laval nozzle, or his converging diverging nozzle, and he's also got a combustion chamber, and he's got a small one. Now, one of the problems with the solid rocket motor is the combustion chamber is typically the entire inside of the rocket where fuel propellant would be. And his idea was to use small cartridges and actually have them fed through the rocket through a complex mechanism. The idea would be the outer skin or outer shell of the rocket could be quite lightweight, and the only part that would have to be thick, heavy metal would be the combustion chamber itself. So novel idea and a nice way to get this actually documented, explained, and actually get a physical date on this from a governing body, in this case, the U.S. government. Recall from section 3 of this video series that Robert Goddard's 1920 Smithsonian publication, A Method of Reaching Extreme Altitudes, documented measurements on the common and constant ship rockets to have a Carnot thermal propulsive efficiency on the order of 2.21% as an average, using a simple orifice nozzle, as shown here. Now, he was able to increase those thermal propulsive efficiencies as high as 64.5% by using a converging diverging nozzle. In his publication, A Method of Reaching Extreme Altitudes, Goddard also shows that he's very aware of the change in air density and gravity as a function of altitude. In his publication, A Method of Reaching Extreme Altitudes, Goddard lists the techniques used to measure things like displacement and exhaust exit velocity. And he also notes that exhaust exit velocities in vacuum are larger than those for air for the same rocket de Laval nozzle chamber size. However, he does not provide a theoretical model for this rationale. He's an experimental physicist and he merely provides results. Goddard's A Method of Reaching Extreme Altitudes, published in 1920, was the first work to describe that rockets do not depend upon the presence of air for propulsion. The contemporary view of the day was that rockets needed to push on air, so this was a very significant leap in rocket research publication. The next thing that he does is he wants to focus on the velocity of expulsion for the propellants. So he really wants to focus on exhaust exit velocity as a means to significantly increase the range for a vehicle. He develops essentially the Tsiolkovsky equation. He adds drag and gravity, and he also notes that he'd like to focus in this upper range between 2 and 3 for delta V over VE, or exhaust exit velocity. And this represents the mass of the rocket plus the mass of the propellant over the mass of the rocket, just like we saw in the Tsiolkovsky equation in section 3 of this presentation. Goddard also clearly listed the efficiency of such contemporary rockets is on the order of 2%, where using a special type of steel chamber and nozzle, this is his de Laval nozzle, that the efficiency has been obtained with smokeless powder of over 64%. So we talked about that in earlier slides. And also, experiments performed at pressures such as probably those existed at an altitude of 30 miles gave velocities even higher than those obtained in air and atmosphere. So he's kind of blazing the way for high altitude rocketry, noting that it doesn't get worse as we go higher in altitude, that rocket thrust actually gets better or increases in magnitude. Goddard's A Method of Reaching Extreme Altitudes also covers a plan to send a massive flash powder to the surface of the moon. His idea was to use the flash powder as the payload, and upon reaching the moon on impact, the flash powder would ignite, which could be verified from the Earth visually, either with the naked eye or with a telescope. So great idea. He also goes through some calculations to show using smokeless gunpowder, he'd need 602 pounds of fuel for every pound of payload that would be sent to, in this case, infinity. This would be to reach escape velocity to be able to leave the Earth's gravitational field. He also does these calculations with his equation, which is very similar to Tsiolkovsky, where he's added gravity and air drag. Additionally, he talks about using fuels that are more energetic, like liquid hydrogen and oxygen, that would have saved him weight for the rocket itself, or made it much more efficient to build a smaller rocket in order to reach the moon. Goddard's publication, A Method of Reaching Extreme Altitudes, was distributed by the Smithsonian Institution on January 11, 1920. By January 12, 1920, the New York Times ran an article, and the headline was, "Believes Rocket Can Reach Moon." Overall, this is a very positive article, and it talks about some of the highlights, such as that instruments could go up 200 miles and bigger rocket might land on satellite. So he's talking about the moon here. And again, very positive article in the New York Times about Goddard's rocket research. The New York Times issues a second article on January 13, 1920, just a few days later, titled "A Severe Strain on Credulity." This goes over the idea of the day that rockets will not function or provide thrust in a vacuum, but then it goes on to attack Goddard's research in general. First, it starts off by stating that Goddard does not know the relation of action to reaction and of the need to have something better than a vacuum against which to react. Then it states Goddard only seems to lack the knowledge ladled out daily in high school. Goddard did not take this feedback well. It took 49 years for the New York Times to print a correction in their newspaper on July 17, 1969. Now, if we look back at history, we note that the Apollo 11 moon launch took off from Kennedy Space Center on July 16, 1969. So thank you, the New York Times. Better late than never. Buzz Aldrin is shown here. He's one of the original Apollo 11 astronauts and the second man to walk on the moon. Buzz chose to take a small notebook with a picture of Robert Goddard on the front to the moon with him in his personal effects. Now you can see Robert Goddard's name is listed here in the heading on the stationery, but Buzz wrote "Flown to the moon on board Apollo 11, July 16 to 24, 1969," and signed it Buzz Aldrin. Now this is a small notebook you can see with respect to a paperclip next to it for scale. But for me, it's interesting to note that Buzz's father actually studied at Clark College under Professor Goddard, where he was introduced to rocket technology. And it's also interesting to note that Buzz's father was the assistant commandant of the Army's first test pilot school at McCook Field, Ohio from 1919 to 1922. And he founded the engineering school there that would later become the Air Force Institute of Technology at Wright-Patterson Air Force Base. So I think it's pretty easy to see that Robert Goddard influenced two generations of Aldrins and eventually helped lead us to the moon. Goddard spends the next several years from 1914 to 1920 working on his cartridge-fed solid rocket motor. The patent is shown here, and we discussed this previously, where he wanted to use a single cartridge that would be fed machine gun style down into a combustion chamber, where the combustion chamber would be the only portion of the rocket that would have to be a thick, heavy metal in order to withstand those pressures and temperatures for the solid rocket motor fuel being burnt and expelled out the back of the de Laval nozzle. Now, while this is a novel idea, it should be noted that Goddard was an experimental physicist, not an engineer, and it was noted by several people that worked with him over the years that he would have been a lot better off trying to hire an engineer to do some of this work rather than doing it himself. So he abandons this technique eventually, stating that the gunpowder exhaust velocity is too low to efficiently reach escape velocity, and he tries to find a simpler technique. And he goes in the direction of liquid fuel plus oxidizer. These typically result in larger heat of combustion values than solid fuel and oxidizer. And remember, as the heat increases, the exhaust exit velocity increases. That means as the heat increases, the thrust increases. So what he's done is he's looking at liquid oxidizer. This is readily available in 1920. And while hydrogen is available in 1920, it's not cheap, and he doesn't have the resources to secure liquid hydrogen. He's doing most of the research at this point out of his own pocket. So this is a personal expense for him to engage in rocket research. So alcohol and gasoline are readily available, and that's the direction he goes in for his first liquid rocket. The world's first liquid-fueled rocket launch occurred on March 16, 1926 in Auburn, Massachusetts at Robert Goddard's family farm. He's shown here standing next to his rocket, and the rocket section itself is on top of the platform. And the green sections are the actual fuel lines and the oxygen lines that supply the combustion chamber. So if we look at the next figure, we can see the rockets on top. That plume would actually come out of the back of the de Laval nozzle. And he's got a heat shield over the top of the oxygen tank. And these tanks are pressurized. So he's got nitrogen pressurizing the tanks to push the fuel up into the combustion chamber, which is shown here. So the fuel and the oxidizer will be ignited in the combustion chamber. They would actually expand out through the de Laval nozzle and cause that thrust that would cause the lift for the rocket off of this ground support platform. So everything we see, the oxygen tank, the alcohol tank, the green fuel and oxygen lines, this would actually take off and leave the ground. Robert Goddard's assistant, Henry Sachs, was the first person to ignite the world's first liquid rocket. And I think that this took a lot of courage. If you look at this system, he's got essentially a pole with a blowtorch on the end, and this is how he ignites the combustion chamber with the liquid oxygen and alcohol fuel to start that combustion process. Now, the altitude for this vehicle was around 12.5 meters with a velocity of 26.8 meters per second. Now, the combustion lasted for 22 seconds, but the flight only lasted 2.5. So for the first 19.5 seconds, this thing sat on this pad structure, this ground support equipment, and burned fuel. Now, as the fuel mass is being expelled, it finally got light enough where that thrust to weight ratio was greater than 1. So when the thrust is greater and force is greater than the weight of force, that's when you get lift and the vehicle will actually leave the pad. So let's detail this ignition process for this first liquid rocket by our courageous Henry Sachs. So he's pointing the blowtorch in this area towards this match head tube. This is a hollow copper tube with a match head in it, and it's adjacent to a steel tube that's packed with black powder. Now the idea is he lights the match head ignites the black powder, and the black powder would actually be expelled into the combustion chamber at a high enough temperature to ignite the oxygen and gasoline or petrol fuel inside the combustion chamber and start that combustion process. Shown here is one of Robert Goddard's early de Laval nozzles that's stored at the Smithsonian Air and Space Museum in Washington, D.C. Now, we note that liquid oxygen and fuel is mixed in the combustion chamber, ignited, and through the converging and diverging nozzle, we end up with a temperature drop down the nozzle that also corresponds to a decrease in density or an expansion in the nozzle. And that expansion and that temperature drop is what creates that velocity change from the throat towards the back of the nozzle and gives us thrust for the de Laval nozzle. Now, Goddard moved from solid oxidizer and fuel to liquid oxidizer and fuel, typically because the heat's higher for these liquid oxidizers and fuels. And we also note that velocity increases with heat, and also as the heat is increased, the thrust. So these are all correlate with each other quite well. The problem Goddard ran into is that heat upper limit is set by the melting point of the de Laval nozzle structural materials, and he noted on his first test that he had melting of the de Laval nozzle, especially around the exit plane of the diverging nozzle. So liquid oxygen was readily available to Goddard in the 1920s. He wanted to use hydrogen, but it wasn't readily available, and it would have been far too hot for the metals he had available to him at the time anyway. But alcohol and gasoline were readily available, and this is what Robert Goddard would end up using. Now, he adopted an approach where he did what's called fuel-rich cooling, as shown here. And what he's done is he's put more fuel into the chamber than there is an oxidizer that can actually combust with that material. So in short, he's unbalanced that redox equation, so it's what we consider non-stoichiometric, which means he doesn't have 99% of the materials, the reactants, forming products. So he's got extra fuel that's not being combusted, that's traveling down the chamber and actually cooling the walls as it leaves the de Laval nozzle. And now, although this reduces thrust slightly, it does cool the chamber to the point where it's below the melting point of the metals that Goddard used for his de Laval nozzle. Combustion chamber and nozzle cooling approaches are shown here. While we noted that Goddard uses that fuel-rich cooling, which allowed for more fuel to be injected into the combustion chamber, then there is oxygen available to stoichiometrically react via combustion, which means that some of the fuel does not get ignited and actually passes through the combustion chamber. Now the problem with this is these fuels are carbon rich, they leave a sooty material behind, and there's carbon buildup on the inside of the combustion chamber and around the nozzle, especially around the exit plane. So while this isn't a problem for a simple nozzle like the one shown here that Goddard used early in his rocket research, as rockets become more and more complex, this will be a problem down the road. So Goddard also looked at oxidizer-rich cooling. This can be a problem with metals. In the presence of high temperature and pure oxygen, metals can get attacked and oxidize quickly, and this can lead to structural defects. So probably the easiest approach is to add water to either your alcohol or your gasoline, that liquid fuel. What happens is as the liquid water changes in phase from liquid to gas, via steam, there's a cooling effect through that expansion of the gas. So as it leaves the plume, it's not going to change its chemistry. It's going to stay water as H2O, but it's going to change its phase from liquid to gas, and there'll be a cooling effect, and that can get us below that melting point of the de Laval nozzle structural materials. Although Goddard has solved his initial problem of high temperatures resulting in melting of the metal materials making up the combustion chamber and converging, diverging de Laval nozzle, his issue is he needs higher combustion temperatures to give him higher thrust. Now his mission is to reach extreme altitudes, and in order to do that, he needs a higher temperature in the combustion chamber. But at the same time, he needs to make sure that the metals he has available to him uh, don't exceed their melting points. So he looks to other technologies, and he comes up with the idea of using an automotive-like radiator. So his idea is to run water through a series of tubes that would be placed on the outside of the de Laval nozzle and combustion chamber to wick heat away from the surface to keep that material below its melting point. So shown here is a clamshell design. So you would take these two pieces, put those together, and put the combustion chamber and de Laval nozzle in between. And that's exactly what's shown here with a series of tubes over the combustion chamber, converging and diverging nozzle. So while this is a wonderful approach and very insightful and innovative, he abandons the work and feels the concept is too complex to implement on a modern rocket. The other problem that he felt was too tough and insurmountable was having to carry the weight of the water that would be recirculated to cool the combustion chamber and de Laval nozzle. Now, um, a modern rocket, such as the RS-25 that's used on the space shuttle and also on the Space Launch System, actually uses a similar approach. In fact, if Goddard would have closed the gaps on all his tubing and brazed them together, he could have actually formed the combustion chamber and converging, diverging nozzle using the tubes themselves. And that's exactly what's done on this RS-25 motor. Looking into the throat from the bottom, we see here 1,080 tubes that are actually brazed together to form the outside of that chamber. So the fuel is actually used instead of water. So the fuel would actually pass through to the bottom of the nozzle, flow up to the top, and actually get mixed with oxidizer at this mixing plate and be ignited in the combustion chamber for that RS-25 motor. So again, Goddard had some wonderful ideas, but had some trouble implementing them on an engineering basis. Now he additionally came up with a spiral configuration, which is very similar to what was used on the Apollo rocket for moon missions in the late 60s and early 70s. So again, very innovative ideas, but very difficult for him to implement. Other researchers are looking at similar approaches to Goddard by using a series of tubes to cool the outside of the de Laval nozzle and combustion chamber. And in fact, Johannes Winkler, a co-founder of the Civilian German Rocket Research Society, VFR, attempted the first liquid fuel nozzle cooling approach in the early 1930s. Now, the problem is his first rocket attempt blew up shortly after ignition, and in the mid-1930s, civilian rocket research was banned in Germany. The only people that were available or allowed to conduct rocket research were for the military, for weapon research. So leading up until the mid-1930s, however, there's a rocket craze in Germany, especially after Max Valier drove this Opel rocket car and actually did several exhibitions showing that the vehicle could be propelled at high speeds using a rocket engine. And here we see they also used water added to their alcohol mixture for fuel. So the idea here was they needed to make sure that the temperature was low enough where they didn't melt the de Laval nozzle and combustion chamber. So you can see that high plume of steam behind the vehicle. Civilian rocket research societies emerged in the late 1920s to early 1930s. Arguably the most influential early on of these rocket societies is the VFR, with the co-founders shown here. Johannes Winkler is a rocket designer, and he's the first to actually consider using liquid methane as a fuel for rocket propellant. Next is Willy Ley. He's a science fiction writer and futurist. And finally, we have Max Valier, who is the driver of the rocket car and an adventurer who's very interested in promoting rocket research in Germany. Goddard and Oberth have a backstory that begins in 1922 and extends through the 1930s. In 1922, Oberth contacts Goddard for a copy of his 1920 Smithsonian paper titled A Method of Reaching Extreme Altitudes for citation in his future book publication, The Rocket into Planetary Space. Goddard obliges Oberth's request and sends him a copy of his Smithsonian paper, and Oberth states he'll cite Goddard as a significant technical contributor to the area of rocket research in his upcoming book. However, in 1923, Oberth lists Goddard's A Method of Reaching Extreme Altitudes as an obscured citation in an appendix of his 1923 book, The Rocket into Planetary Space. So what we see on the left is Willy Ley, a co-founder for the VFR. He flees to the U.S. in 1935 from Nazi-occupied Germany, and he champions what's called TGO, or this is Tsiolkovsky-Goddard-Oberth rocketry. And this means that all three of these gentlemen were significant contributors to the area of rocketry. And he makes the quote that ideas like large rivers never have just one source. Now, Willy Ley also becomes a U.S. citizen in 1944. Now, on the right, we've got Hermann Oberth and Max Valier, who are very pro-German when it comes to rocket research. So they would like to make rocket research more of a German national research effort. And you can really see there's a chasm between these two camps when it comes to this lifelong feud. VFR translates roughly into English as Society for Space Travel. Johannes Winkler is the VFR president from 1927 to 1929, along with his co-founders Willy Ley and Max Valier. Valier reads Oberth's book, The Rocket into Planetary Space. He meets with Oberth to discuss the future of German-led rocket research, where a strong collaboration is established. Now, Oberth joins the VFR as president in 1929, where Winkler steps down and is given a smaller role at the VFR. In 1930, the VFR has around 500 volunteers, many of whom are students, including the 18-year-old Werner von Braun, as shown here with Hermann Oberth conducting rocket experiments. The VFR functions from 1927 to 1929 as a civilian rocket research agency staffed by volunteers and funded by donations. As such, their limited financial resources made it quite difficult to perform significant rocket research efforts. This changes when science fiction filmmaker Fritz Lang funds the VFR as consultants to build scale models for his movie Frau im Mond, which translates as Woman in the Moon. Specifically, he hires Dr. Hermann Oberth to lead this effort for the VFR, and this keeps the VFR afloat in funding from 1929 to 1933. Fritz Lang also came up with the ubiquitous 3-2-1 countdown sequence to add drama to the ignition sequence for the rocket. Robert Goddard's first liquid-fueled rocket launch was conducted on March 16, 1926 from his family farm in Auburn, Massachusetts. Over the next several years, he conducts several launches in secret with his grad students from Clark College. Now, on July 17, 1929, one of the rockets launched from Auburn, Massachusetts explodes in air. Several neighbors call police, where several police cars and 2 ambulances are dispatched to the family farm. Now, Goddard explains upon their arrival that he's been conducting experiments on rockets, and it was well known from a Smithsonian publication that he believed he would ultimately result in sending a rocket to the moon. Now, at the same time period, around that time in 1929, German researchers from the VFR are working with Fritz Lang on the movie Frau im Mond, or Woman in the Moon. And they believe they're the first researchers to work on liquid propellant rockets at this time. The Boston Daily Globe picks up on the local story on July 17, 1929 regarding Goddard's rocket explosion in Auburn, Massachusetts. Now, this makes it out to more of a national news story, and eventually the New York Times reports a similar article where Charles A. Lindbergh, famous for the first nonstop transatlantic flight between New York City and Paris on May 21st, 1927, reads the newspaper article about Goddard's rocket test in Auburn, Massachusetts. So Lindbergh contacts Goddard via mail to set up a meeting to explain his rocket testing and research in more detail. This leads Lindbergh to eventually introduce Goddard to philanthropist Harry Guggenheim. Goddard's rocket research from 1929 to 1938 was primarily funded from a $50,000 donation from Harry Guggenheim, where Goddard focused on building the first rocket motor liquid fuel and oxidizer pumps designed and built at his facility in Roswell, New Mexico. Now, Goddard realized that in order to increase the combustion chamber pressure and mass flow rate, which would give him more thrust through the de Laval nozzle, he was going to need pumps to do that. And he used an innovative technique using a steam turbine drive on both the fuel pump and oxidizer pump to dramatically increase the mass flow rate and pressure for the supply oxidizer and fuel. Now, while Goddard did show that this significantly increased thrust for the de Laval nozzle, he did not devise and demonstrate a plausible solution to drive the pump turbines on a rocket motor in flight. Robert Goddard's first publication with the Smithsonian Institution, A Method of Reaching Extreme Altitudes, was a true paradigm shift in rocket thrust efficiency, where he's able to take the Carnot thermal propulsive efficiency using an orifice nozzle and boost that from 2% to near 70% using a de Laval nozzle. So this dramatic increase in thermal propulsive efficiency helped launch a volunteer rocket R&D community worldwide in the late 1920s through early 1930s, starting in Germany, Russia, United States, and Britain. So Goddard's first successful liquid-fueled rocket launch was on March 16, 1926. However, Goddard doesn't publish this work until 1936. Again, still great work, but late to publish, and many, including the VFR in Germany, moved to liquid propellants in the 1920s. In fact, the VFR will have their first successful liquid propellant rocket launch in January of 1930. Goddard's contributions to the area of rocketry is certainly significant, but could have been so much more impactful. Goddard chose U.S. patents as a mechanism to document his technical research efforts, with over 200 patents issued and 100 of those submitted posthumously by Goddard's wife Esther, who also served as his videographer and photographer during his rocket research experimentation. Now, Goddard's first journal publication, A Method of Reaching Extreme Altitudes, although a significant paradigm shift, was delayed by several years after the completion of his experiments, only after significant encouragement by the director of the Smithsonian Institution and his academic advisor at Clark College. His second journal publication, Liquid Propellant Rocket Development, was delayed by almost a decade and could have been a huge paradigm shift if published before 1930. Now recall that first successful VFR liquid-fueled rocket was launched on January 25th, 1930 at Halen Works in Germany. And in closing, Theodore von Kamenn, the lab director at Caltech, notes that Goddard could be quite difficult to collaborate with regarding rocket research. An early liquid cooling technique used to increase rocket thrust is shown here from 1938. Liquid fuel is pumped into the back of the rocket near the de Laval nozzle through a hollow cavity which also passes by the combustion chamber, where at the top of the rocket it mixes with liquid oxygen to form an oxidizer and fuel mixture. That mixture is ignited by an automotive spark plug, and higher combustion temperatures can be achieved using this technique because of the local cooling due to the fuel pulling heat out via conduction through the inner wall of the combustion chamber. Now that heat, which otherwise would have been waste heat, is also regenerative. So that heat is moving up to the top and back into the combustion chamber. So that waste heat that would have passed out through conduction to the ambient is reintroduced and can be used for additional thrust. Also, the combustion chamber temperatures can be higher because of that local cooling effect. So this is a win-win solution for additional thrust with respect to regenerative heat. Now this is introduced by James H. Wild of Reaction Motors Incorporated. Now the actual rocket motor is very small. It's approximately 5 inches on a side or 12.7 centimeters from collar to collar. And you can see the collars here in the picture at left. Now, again, a fairly small demonstration, and James Wildwood was working with the American Rocket Society, who published this work in 1938. If we look at the rocket motor, what you'd see is fuel would flow in through the bottom, through the de Laval nozzle, up the side combustion chamber walls, and then mix with the liquid oxygen inlet at this point. And there would be an automotive spark plug screwed into this fixture at top to ignite the fuel mixture inside the combustion chamber. The world's first regeneratively cooled liquid rocket motor is shown here as demonstrated by Wild and published by the American Rocket Society in 1938. A similar approach was adopted on the large scale by the German A4 rocket team, later to be named V2, and was co-designed by Walter Thiel and Arthur Rudolph, with its first successful launch test on October 3rd, 1942. Now they flowed fuel, which was alcohol in this case, into the back of the rocket near the exit plane of the de Laval nozzle, where it would flow through a hollow cavity channel, picking up that heat on the interior wall of the de Laval nozzle combustion chamber and dump that heat back into the combustion chamber as it mixed with liquid oxygen to form that liquid fuel and oxidizer. Now this was ignited by a spark device very similar to a spark plug. So again, very similar approach on the German A4V2 team and Wild's approach in 1938. Liquid cooling with fuel injection innovation was demonstrated by the German A4V2 team. The first major innovation is they introduced the fuel pump and liquid oxygen pump driven by a steam turbine as proposed by Goddard and tested on a tabletop setup. Now, Goddard never flew this, but what the Germans have done is they figured out a way to create a steam generator that's light enough and strong enough to drive that steam turbine that can significantly increase the fuel pump mass flow rate and internal pressure inside the combustion chamber. So significant improvement and big step for rocket technology. Now, the next thing that they've done is they've implemented Wild's technique of cooling using that hollow wall on the back of the de Laval nozzle up through the throat and up towards the combustion chamber, where at the top it mixes with the liquid oxygen in one of these burner pots. And if we look at the top of the device, there's 18 of these burner pots. And if you look at one of the inlets of one of those pots, liquid oxygen would actually come in through this inlet, and this would be a hollow fuel cavity. So this is a cutaway shown here. So there'd be fuel on this side that actually would get pressed through at high pressure and inject and spray into the nozzle. So the fuel would inject and spray out in this direction, and the oxygen would spray out in this direction. So it would actually be radiating from one of these inlets at the top and be impinged on the side from one of these injectors for fuel. So if you're interested in a video that explains this in more detail, Scott Manley has a great rocket fuel injector video as shown here with the YouTube link. Now, the next thing that they've done that's significant is the Germans have introduced a fuel-rich flow. So because they have a hollow cavity with fuel on the side, they've put a few injectors on the sidewall. And what that does is it introduces fuel into the cavity that won't be combusted, and that actually helps cool the wall as well during the combustion process. The pump turbine is driven via steam power for the German A4V2 rocket. We note that if we look at the steam turbine, there is a steam generator located above it. Now this steam generator is comprised of high pressure nitrogen tanks that provide pressure to the liquid peroxide tank to push that liquid peroxide down into the sodium permanganate and sulfuric acid chambers. Now this results in a significant and rapid release of steam, which drives that steam turbine to drive these liquid oxygen and fuel centrifugal pumps, also known as turbo pumps, up to a high mass flow rate and pressure. Now that high pressure is important. What we note is for the V2, they were able to get near 25 atmospheres inside the combustion chamber. And at the exit of the combustion chamber, and de Laval nozzle, especially at the exit plane for the de Laval nozzle, we see that their goal is to get near 1 atmosphere. Now that's showing that pressure drop from 25 atmospheres to 1 atmosphere, which would be ideal for a fully expanded nozzle. Now, there's a significant increase when we get above 10 atmospheres in the combustion chamber. So it's very difficult if you use just pressurized nitrogen to push your fuel out to get above 10 atmospheres. And using these fuel pumps and LOX pumps, what we see is the Germans were able to get to around 25 atmospheres. And again, when we get above 20, we see there's a significant increase in efficiency for thrust. Note that as the pressure in the combustion chamber is increased, thrust also increases, but there is a diminishing return when you get above 20 atmospheres. So very significant from 0 to 10, still significant 10 to 20, and not as significant above 20. So again, we like to be above 20 atmospheres as a minimum in the combustion chamber to make sure we're getting efficient thrust through the combustion process. Gyroscopes developed for the guidance system on the German V2 rocket were designed by Dr. Fritz Mueller. Now this is a pendulous integrating gyroscopic accelerometer, and it's shown here with the internals shown with the cover off in this figure. Now the components are comprised of a spinning circular mass that's spun up to a high rate of speed using an electric motor, and Mueller's first design used ball bearings for the gyroscope spin axis. Now, once this is rotating at a high rate of speed, any rotation, the gyroscope will want to stay at its initial point in space. So from that, we actually have that reference point. Just before launch, these are spun up to a high rate, and they'll resist movement during the course of the launch of the rocket from launch pad to target. Now, how the sensor is used, or that gyroscopic sensor is used for feedback, is these thrust vector control vanes. These are carbon vanes that are placed in the exhaust plume of the de Laval nozzle. And although Goddard was the first person to demonstrate this, the German team is really the first to demonstrate it on a flying vehicle with a high rate of accuracy from launch pad to target. So during ascent, they use these thrust vector control vanes, which are carbon vanes placed in the exhaust plume of the de Laval nozzle. And during descent, after they've gone past the Kármán line and have re-entered the Earth's atmosphere, they're going to use air rudders to do their steering, again using that gyro feedback from the guidance system. Three major technical innovations of the A4V2 rocket development teams is shown here. The first has to do with centrifugal turbopumps plus the steam generator as the pump power source. We note this is outsourced R&D, where the V2 team hires a company called KSB, or Klein, Shanzen, and Becker, to develop the V2 liquid fuel and liquid oxygen pumps. Now, this company KSB, they've focused on building pumps for German fire departments, and as such, they're very good at moving water at high pressure and high mass flow rate. So very good choice to design these pumps for the German V2 team. Now the steam generator power source, this is outsourced to Helmuth Walter of Walter Works, another German company. Now the item 2, regenerative cooling of the de Laval nozzle metallic surfaces using liquid rocket engine fuel. This is external R&D. In fact, they've noted that James Wild of Reaction Motors Incorporated has a technical journal publication with the American Rocket Society in 1938. That describes moving fuel into the back of the rocket near the de Laval nozzle exit plane through a hollow cavity up to the top of the rocket, such that heat can be re-entered or regenerated into the combustion chamber, and also lower the temperature of the combustion chamber walls below that melting point for the metallic surfaces used. Now, while Wild used a simple technique to mix liquid oxygen and fuel, the Germans have done a much better approach in their mixing approach, where they have fuel coming in the bottom of the rocket, going up the hollow cavity up towards the top of the rocket. But here they've used jets to impinge on the liquid oxygen as it comes in, and they've done a very nice approach of getting a very good mixing of their fuel and oxidizer pre-ignition. So, and here we can see some of the complexity with the burner pots, with the silver line showing the oxygen line inputs, and these lines showing the fuel as it would flow up towards the burner pots and mix with the liquid oxygen. Last, we look at gyroscopes for attitude control during powered flight and guidance to target, and this is outsourced to Kieselgerät, another German company, and this essentially translates to gyroscope. But again, major innovation, and without these gyroscopes for feedback control in the guidance system, using this as a weapon during World War II would have been near impossible. The four main German rocket scientists can be listed as Walter Dornberger, Werner von Braun, Walter Thiel, and Arthur Rudolph. Now, if we look at the first picture, we see a General Walter Dornberger standing next to Werner von Braun. And off to the right side of that picture is Walter Thiel. Now, these gentlemen have a very complex relationship where Dornberger is the administrator for the Peenemünde site and the rocket development activity. So he's in charge of everything. Reporting into him is Werner von Braun. Now, von Braun is in charge as a director of all the technical operations for V2 rocket development. And he's got his deputy director as Walter Thiel. Now, Walter Thiel, he is dealing with the day-to-day real technical operations, whereas Werner von Braun, who's also an SS major, who rarely wears his uniform, his job is more or less to deal with the military funding agencies and make sure that everyone is aware of the research and is happy with the progress. Now, Walter Thiel is dealing with the day-to-day activity, and Arthur Rudolph, shown here, is the rocket designer for the engines. So between Walter Thiel and Arthur Rudolph, this is where the real technology is happening in the innovation. Again, Werner von Braun is the technical director, and Walter Thiel and Arthur Rudolph report into him, and Werner von Braun reports directly to Walter Dornberger. Werner von Braun led a team of 20,000 individuals with greater than 5,000 engineers and scientists at Peenemünde, Germany from 1938 to 1945. The German military and government interpreted the World War I surrender conditions defined by the Treaty of Versailles as not to explicitly ban Germany from rocket weapon development. Peenemünde focused on V-1 jet for the Luftwaffe or Air Force and V-2 rocket weapon development for the Army. Now, a picture of Peenemünde is shown here, and that Air Force region of Luftwaffe is shown at top with a V-1 catapult. The rest of the base is pretty much set up for the Army, and they're focused on V-2 launch. And the launch pad and the facility is actually shown here. So the rockets would be built up in this building, would roll out to the pad, and then be fired from this location. And you can see the flame trench for the exhaust actually shown here at the pad facility. So this is the world's first top secret black site for military weapons research. And later in development, Arthur Rudolph writes a memo to von Braun asking for imprisoned concentration camp laborers around 5,000 to supplement V2 production workforce at Peenemünde. If we look at the Peenemünde base, we notice there's a concentration camp on base next to the Army barracks. So they use concentration camp detainees to work on V2 production development. And again, the funding for the German military, they provide over $1 billion in 1943 funds to develop ballistic missiles, primarily at Peenemünde as an R&D facility. British aerial reconnaissance photographs the top secret R&D facility at Peenemünde during mid-1943. As a result, Peenemünde site is bombed by Allies on August 17th and 18th, 1943, under the Allied bombing campaign named as Operation Crossbow and Sub-Operation Hydra. Now, Walter Thiel is killed during the Allied bombing raid in 1943, and as a result, V2 manufacturing is moved from Peenemünde to Mittelwerk, in an underground gypsum mine in the Harz Mountains near Berlin from 1943 to 1945. Now, the Peenemünde staff will eventually be evacuated to Bavaria via rail train on February 17th, 1945. But from 43 to 45, they continue their efforts to work on motor optimization on their test stands and V2 rocket launches from the launch facility at Peenemünde. The V2 rocket manufacturing facility is moved from Peenemünde to Mittelwerk, a gypsum mine in the Harz Mountains, which is safe from Allied bombing raids. Arthur Rudolph will be transferred from Peenemünde to Mittelwerk, where he'll be responsible for V2 technical production line efforts. SS General Hans Kammler, shown here, is a civil engineer, and he's in charge initially of site construction and the imprisoned laborers at the adjacent Camp Dor Mittelbau. Now, eventually, he'll assume administration production responsibility, where he'll be in charge of the entire facility, including Rudolph and von Braun. Now, the laborers from Camp Dora Mittelbau are used to dig the tunnel system at Mittelwerk. This is around 60,000 prisoners, and approximately 20,000 of those laborers died on site due to terrible working conditions and harsh treatment, including starvation, beatings, and multiple executions from German captors. Now, approximately 1 out of every 3 laborers die building V2 rockets at Mittelwerk, while 9,000 lives are claimed in areas local to London that are killed by the rockets exploding. So in short, more lives are taken building the rockets than they are by the exploding rockets. Now, Camp Dora is liberated by Allied American forces on April 11, 1945. V2 rocket impact on World War II's outcome was minimal at best. Around 1,500 V2 rockets reached England during World War II on a 7-month span from September of 1944 through March of 1945. Early production V2 rockets failed at a percentage of near 80% due to a Max-Q structural flaw during ascent. Now, the targets and casualties average around 3 fatalities, mostly civilian, per V2 rocket launched. The average range to target is approximately 320 kilometers or 200 miles, with an air radius accuracy of around 12 kilometers or 7.5 miles. This is an interactive map that shows some of the impact sites around London, and this is a picture of an actual impact site. Early production V2 rockets have a major design flaw located in the thrust frame. If we look at an early production V2 motor, we note that the thrust frame sits above the motor and transmits all the force during ascent or burn to the fuselage above. Now, during max Q, where the max load's put on the vehicle, these small diameter thrust frame posts would buckle on about 80% of the rockets. So in late production 1944, the diameter was significantly increased to handle that load. So the percentage of rockets that were successful went from around 20% success rate to around 90% success rate with this late production model. But again, this is too little too late in the war effort to have a significant outcome. Peenemünde and Mittelwerk staff were evacuated to Bavaria on February 17, 1945. A group of key German rocket engineers and scientists contacted U.S. forces in the Munich area to arrange a group surrender during May of 1945, primarily to avoid Russian capture. These engineers and scientists were individually interviewed and screened for high technical value regarding subsequent transport to a U.S. Army base, this is Fort Bliss in Texas, for U.S. rocket research activities. Now, 104 of the engineers and scientists have their intelligence dossiers marked with paper clips to designate high-value candidates for U.S. transport. So in essence, as one of the intelligence officers stated, significant World War II war crimes were waived, ignored via paper clips in this case. Now, if we look below, we note that Werner von Braun is next to Dornberger. Von Braun would go on to lead the manned space program at NASA, starting with Redstone through Mercury, Gemini, and Apollo. And Dornberger would go on to become a vice president at Bell Aircraft Corporation. So additionally, Rudolph would follow von Braun, and he would develop rocket engines for most of those manned space programs as well, including the Apollo program. But in 1983, he's deported from the United States based on suspected World War II war crimes after a long career with NASA under von Braun's leadership. Military Operation Paperclip brings these German rocket engineers and scientists to Fort Bliss, Texas, as shown here. Now, from a technology standpoint, this represents a leap in the United States capability for rocketry, as many of these engineers have experience that goes back as far as 1930 at Halent Works or 1938 through 1945 at the R&D Technical Center at Peenemünde. Operation Paperclip engineers well documented rocket thrust parameters from 1938 to 1945. Now, after World War II, they share this information with U.S. engineers on velocity, acceleration, and mass as it pertains to the exhaust combustion products that leave the de Laval nozzle at the exit plane area. Now, the exit plane area for that de Laval nozzle for the German V2 rocket is shown here, where RE is the radius of that exit plane. Now, the area is pi r squared, and this is the pi times the radius of the exit plane squared. Our goal is to derive thrust as a force equals F directly from Newton's second law of motion as shown here. We'll find it's easier for us to solve this differential equation if we redefine the mass of the exhaust as it crosses the de Laval nozzle exit plane in terms of VE. And that's precisely what we do in this step, where we see it's a function of the density of the exhaust gas, the rocket's de Laval nozzle exit plane area, the velocity of the exhaust gas at the exit plane, and the time elapsed in seconds since the rocket fuel oxidizer ignition, which represents the duration of combustion for the rocket motor. Now, the next step is to take the mass flow rate, and this is the first derivative of the mass of the exhaust as it crosses the de Laval nozzle exit plane with respect to time. And we note that time is dropped out with that first derivative, so we end up with an even simpler relationship. Now, our step will be to take this value for ME and place that directly into this portion of the equation, and take this value for the first derivative of ME with respect to time and place that into this portion of the equation. So, and now we have the differential equation in terms of VE for both parameters. Newton's second law of motion states that force is equal to the change in momentum delta P per unit change in time delta T. If we take the momentum to equal the mass of the exhaust times the velocity of the exhaust, and we take that first derivative of momentum with respect to time, we get force in units of newtons. This tells us the thrust at the exit plane for the de Laval nozzle. And we note that that dme VE dt, that first derivative, needs to be expanded out with the product rule in calculus. Now this was defined previously in video 1 on slide 18. So this force is going to be important, and we see it down in the equation below. And what we're going to do is we're going to plug in dme dt, as shown here, in front of the first parameter, and we'll plug in me, this parameter, for the second parameter in the equation. So we immediately note that there's a delta t still left in the terms. So if we multiply both sides of the equation times delta t, which is done in this next step, we're left with this result. Now we set up the integrals to get rid of those differentials, and we're left with the next line in the equation. Once we complete the integration, we're left with this value where we see we have a function of time in each parameter. Now, if we divide through by time, we're left back with a force, and we end up with this simple result. Now, from Bernoulli's equation, we also note that rho times v squared, or VE squared over 2, is also the dynamic pressure. So we know that this is going to be the exit pressure, or the pressure at the exit, due to VE, or this exit velocity flow at the opening of the de Laval nozzle exit plane area. So with this simple result, we're able to actually write the equation for force as a function of thrust in units of newtons, as shown here. So with Newton's 3 laws of motion, we note that for case 1 at vacuum or high altitude, P0 equals 0 pascals, or essentially we're at vacuum, and we have no force pushing back into the de Laval nozzle exit plane area, and no modification of Newton's second law is required, and we're left with this simple result for force as shown here. Case 2 represents operation of the rocket motor at a 1 atmosphere static pressure ambient, represented by P0 equals 101.325 kilopascals, and this corresponds to a force that will try to push back up into the de Laval nozzle exit plane area as a function of that static ambient pressure P0 times AE, the exit plane area of the de Laval nozzle. Now, this direction of force is opposite to the mass flow rate and exhaust velocity, so we need to subtract that from our forcing function as shown here. So it's still that first derivative momentum with respect to time minus P0 AE. Distributed out, it would look like this, and if we plug this into our function as shown below and follow through as shown on the previous slide, we see that the result is going to be shown here by that m dot VE plus the exit pressure. This is that dynamic pressure at the exit plane of the de Laval nozzle minus the static ambient pressure times the area of the exit plane. Case 1 and 2 can be combined into a single case as shown here, which addresses P0 at 0 for vacuum through 1 atmosphere at ambient pressure at sea level. Note that this is exactly the same result we got for case 2 in the previous slide, and the force of thrust is shown by this relationship. Now, PE, again, is the exit plane dynamic pressure located at the exit plane of the de Laval nozzle, and P0 is the static ambient pressure just outside that de Laval nozzle area. So we also note that we can rewrite this in terms of PE and P0, or we can leave it in terms of VE, as shown here. Note that these two equations are equivalent. Rocket motor thrust can be described by a force as shown here, with two major cases for the static ambient pressure P0. The first case would be sea level at near 1 atmosphere, where we would actually define for both cone and bell-shaped de Laval nozzles an exit plane dynamic pressure PE equivalent to the static ambient pressure P0. When that's done, we're left with a fully expanded nozzle, and this term drops out to 0. This means that the entire force magnitude is defined by the mass flow rate times the exhaust exit velocity as shown here. Now in the case of a vacuum, we're left with no ambient pressure, or 0 for P0. So the force is essentially PE times AE plus m dot VE, and we have around 1/3 of the magnitude responsible for force due to that exit plane dynamic pressure PE. Also note that all vacuum reference de Laval nozzles are underexpanded by definition. De Laval nozzles can be designed at sea level to be one of three cases. It can either be overexpanded, fully expanded, or underexpanded. Now, the most efficient thrust condition transfer of momentum occurs for a fully expanded nozzle, but this doesn't necessarily mean the highest thrust. So what we would note is typically for the same nozzle, you're going to have thrust increase from overexpanded to fully expanded through underexpanded. And essentially what we see is as altitude increases, we transition from these three phases as well. So for a low altitude first stage motor, we would typically want to start with near a fully expanded motor and have it transition to an underexpanded motor as it actually reaches a higher altitude through vacuum. This is going to give us the most efficient use of thrust over that range. When you see a motor that's overexpanded at low altitude, it's typically tuned for higher efficiency at higher altitudes, where it'll transition through from overexpanded through its fully expanded regime when PE equals P0 to underexpanded at high altitude. The Space Shuttle has two major thrust systems for rocket motors and rocket engines. The first would be the solid rocket boosters shown here. And these two solid rocket boosters are slightly overexpanded at ignition. We'll consider them to be fully expanded at 1 atmosphere. And they transition through that underexpanded phase as they move through high altitude before being jettisoned around 45 kilometers in altitude. So again, we'll consider that case to be fully expanded through underexpanded. So now the second case is the RS-25 liquid rocket engines as shown here. Now they start off as being quite overexpanded at sea level. So if we look at that overexpanded flow through the motor, this would represent the central streamline, which crosses the de Laval nozzle exit plane area at 90 degrees only for the central streamline. These other streamlines are going to cross at an angle less than 90 degrees as shown here. Now, what that means is we're going to see shock diamonds because these are going to be pushed in from that ambient external pressure, and they're going to cross multiple times in the thrust plume as shown here. So this represents energy waste that could have been efficiently converted to thrust in the motor if it was fully expanded. So the next phase is fully expanded. So at a given altitude, the external dynamic pressure will be equivalent to the ambient static pressure, and we'll end up with this very efficient thrust condition for the motor. So this happens at a much higher altitude for the RS-25s, and eventually when we get near a vacuum condition, it'll be underexpanded. Now, the important thing to note here is that even for the RS-25, the thrust is increasing from overexpanded through fully expanded to underexpanded. And if we look at the values, the force of thrust is less than 2 times that dynamic pressure times the area of the exit plane for the de Laval nozzle at sea level, and then it transitions to 2 times that pressure, that dynamic pressure times the area of the exit plane area at full expansion, and it's just under 3 when it's underexpanded at altitude. So again, that trend shows us that thrust is increasing as pressure is decreasing as a function of altitude. Now, why is that occurring? If we look at the streamlines for the flow of the exhaust gas as it crosses the de Laval nozzle exit plane as shown here. And this is a zoom at this location. So what we note is the force vector only for the central streamline for an underexpanded nozzle is actually pointing directly with a 90-degree angle to the flow out of the nozzle. So if we look at the other values from here to the edge of the nozzle, we note that there is a 90-degree angle here, and we would have to take the average of that theta between 90 and whatever this maximum angle is, sum that up, and that's going to give us a lowered thrust value. Now, the thing that's helped us here is the lack of ambient pressure has also increased the force of thrust. So there's 2 competing mechanisms here. One is the decrease in thrust due to this non-90-degree angle across most of the nozzle, but the increase in thrust due to the lack of external ambient pressure. So what we need to note is there is a significant increase from ambient static pressure at 1 atmosphere to the vacuum condition for that RS-25 motor. In fact, if we looked at the thrust at sea level at 1.86 meganewtons, and we look at the thrust at vacuum at 2.28 meganewtons, we note there's around a 22.6% change in thrust from sea level to vacuum for that RS-25 engine. Figure 3-11, simplified diagrams of different generic nozzle configurations and their flow effects, was extracted from the textbook Rocket Propulsion Elements as shown here. Note that previous slides in this presentation showed cone and bell de Laval nozzles of near equal length, while we note that for most modern de Laval nozzles on rocket engines, we note that they are compact bell designs. Now the rationale is there's a significant reduction in length possible by going to a compact bell, and this represents a mass reduction on the order of around 25% as compared to a full-length bell. Now the trade-off is when we go from a gradual slope on the full-length bell contour, we see that there's a much more difficult to fabricate shape on the compact bell. So higher complexity in manufacturing, but a significant reduction in length that corresponds to around a 25% mass reduction. So this is worth it for most modern day rocket designers. So again, we're going to note that most modern designs are focused on the compact bell. If you're interested in additional types of rocket nozzles, especially the Aerospike, I would highly recommend Tim Dodd's video on Aerospike's the SSTO single stage to orbit on the Everyday Astronaut website. The Space Shuttle's RS-25 liquid rocket engines are shown here. The perspective view would be more along this axis where we see a solid rocket booster in the background and we see the 3 motors as viewed here. Now this is an 18-second video that represents around 10 seconds of real-time RS-25 ignition while the vehicle is still attached to the pad via the solid rocket boosters. So the hold-down posts for the solid rocket boosters have not been separated from the mobile launch platform, and the solid rocket boosters have not yet been ignited. Again, this represents around 10 seconds of burn time. So now what we would note is that while the RS-25s are ignited at sea level, they're slightly overexpanded. In fact, when they light, there'll be a little flow separation until we get that stable flow around the edge of the RS-25 engines. So if we watch the video, we'll note that we also get a mode shape in the vertical and horizontal modes. So again, flow separation, there's that mode shape. It's going to dampen out pretty quickly. And then we get stable flow for the rocket motor. And that mode shape damping is pretty typical for these bell shapes as they have a pretty low frequency fundamental mode. So the next thing we note, as the RS-25 transitions through altitude, it's going to go through its fully expanded region and then eventually make it to an underexpanded motor where it's very efficient and has a high thrust condition. Now, the one thing we need to note is flow separation. It can be a dangerous event. You can see it also in this rocket motor here. And when you can see into the nozzle, the danger is pressure can push in from the outside, atmospheric pressure. And if this is at a significantly lower pressure than atmospheric, which is the case here, it can violate or exceed the structural integrity of the nozzle. And this can result in catastrophic failure of the de Laval nozzle if it's not strong enough to withstand atmospheric pressure at the lower pressures for the dynamic exhaust. So this is an important feature that we find highly undesirable for a rocket motor. Again, overexpanded is okay and acceptable, but highly overexpanded at 1 atmosphere is a highly undesirable event that can lead to catastrophic de Laval nozzle failure. Flow separation in an overexpanded de Laval nozzle still is a hot topic of research, and this YouTube link shows some interesting work done at Stanford on converging diverging de Laval nozzle. Now note, it's interesting to see the separation zones at the edge of the nozzle, and they also describe a reduced order modeling technique to significantly reduce the computer load to simulate these results. Also shown is a method to visualize the actual experimental results where you can see flow separation as well. De Laval nozzle flow separation can be estimated using simple hand calculations. A recent conference paper titled Flow Separation in Rocket Nozzles, an Overview, was published in 2013 with the information shown here. Now, references were listed from 1948 through 2010. And the one I gravitate towards is the Summerfield and McKenney reference from 1954 because it's very easy and compact to use. Now, what we note is it lists the separation pressure of around 0.4 for the ambient pressure with respect to the dynamic pressure. So when the dynamic pressure reaches about 0.4 ambient, you can pretty much estimate that there'll be a separation condition for your de Laval nozzle. So this is valid for an alpha of, which is the ratio of specific heats as shown here, ranging from 1.2 to 1.4. And this is a pretty typical range for solid and liquid rocket motors. While rocketry is going through the next phase of rapid technological innovation in Germany from 1938 to 1945, Robert Goddard is effectively sidelined by the U.S. military during World War II to work on jet-assisted takeoff of large aircraft on short runways. Now, while this should have been called rocket-assisted takeoff, the word rocket is not well received by the U.S. military from the 1920s to 1940s, and projects are typically renamed jet instead. So this used small rocket engines attached to the outside fuselage of large bomber aircraft so they could take off from short runways during World War II. Now, towards the end of World War II, Robert Goddard is asked to inspect a retrieved V2 rocket turbopump, where he conveys that it's a significant improvement over his original 1938 turbopump design. Now, shown here is a picture of Wernher von Braun in 1946 at the White Sands, New Mexico facility where the U.S. launched multiple V2 rockets shipped back from Germany at the end of World War II. Now, during September of 1945, von Braun is brought to the U.S. via Operation Paperclip, where he's debriefed by Bob Truax. Now, Robert Truax is probably the most influential American rocket engineer that you probably never heard of, but you can see he's got quite a significant past where he essentially also pitched and designed the Polaris ICBM. This is the first intercontinental ballistic missile launched from a submarine and was in service from 1961 to 1996. He was also president of the American Rocket Society in 1957. So Bob Truax, while he's in the Navy at the end of World War II, he's asked to debrief von Braun. Now, he asks in-depth technical questions, and his takeaway from their meeting and their debrief is that while von Braun understands the big picture from an administration standpoint, he is not a design engineer when it comes to rocketry. So very interesting take from Mr. Truax on this particular topic. Von Braun is relocated to the United States in September of 1945, as shown here. Now, von Braun, he surrendered to U.S. forces, and we see a U.S. soldier in the background here behind General Dornberger on May 2nd, 1945 in Bavaria. Now, it's interesting, these two become prominent members of the American aerospace community. Von Braun would obviously go on to help design all the rockets used in the U.S. manned space program, and General Dornberger would go on to be a vice president at Bell Aircraft, where he would help design and manage the world's first aircraft to break the sound barrier. While von Braun is responsible for the design of multiple spacecraft during the 1950s and 1960s for the U.S., he himself is not doing the day-to-day design activity. He's managing the design engineers. And in fact, we see here is the single U.S. patent filed by von Braun in 1952 with respect to an experimental spacecraft. Now, shown here is multiple U.S. rocket administrators and engineer scientists. And if we start in the back, this is Major General Holger Toftoy. He was responsible for retrieving V-2 rockets at the end of World War II, bringing them to White Sands, New Mexico, and extracting as much information about the German rocket program as possible and transferring that to the U.S. military. He stayed active in rocketry throughout the 1950s and 1960s. And worked quite frequently with Wernher von Braun, as shown here. Now shown at this location is Ernst Stullinger. He was an Operation Paperclip rocket guidance design engineer, and he was key to the manned space program guidance system design and development in the 1950s and 1960s through the Apollo program. And shown in front is Hermann Oberth, who had a significant impact on young von Braun to explain basic rocket concepts. Now we transition into the 1950s, and we see that Walt Disney is standing with von Braun. In fact, the relationship between these two gentlemen was so strong that it influenced Disney to open Tomorrowland. And if you look at a V-2 rocket, even the shape of the fuselage of the rocket is quite similar to that rocket that was placed in Tomorrowland on its opening on July 17th, 1955. Wernher von Braun's timeline is shown here from the 1940s through 1950s. We start in the mid-1940s, where von Braun is able to gain continued financial support from the German military. And in fact, during this period, he holds the military rank of major in the SS, but rarely wears his uniform in public. In 1945, he surrenders the U.S. troops in Bavaria with General Dornberger, and this leads to his relocation to White Sands Proving Grounds, New Mexico, where multiple German V-2 rockets are brought back from Mittelwerk and Peenemünde research facilities in Germany after World War II to help transfer that technology to the U.S. military. Now, in the 1950s, he strikes up a significant relationship with Walt Disney, where they produce 3 specials on television to describe the future of American rocketry. This leads to the perception that von Braun is the face of future American rocketry and gains him access to meet President John Fitzgerald Kennedy on multiple occasions, where the two gentlemen strike up a fairly close relationship. Rockets used to launch humans into parking orbits are shown here from 1961 through 2020. Now, if we note from the early 1960s through the 1980s, 2 countries are primarily responsible for launching humans into space. And that'll be the United States and Russia, or the Soviet Union. Now, we also note that the American program was led by Wernher von Braun, and the Russian or Soviet Union program is led by Sergei P. Korolev. In the early 1930s, Sergei P. Korolev studies aeronautical engineering in Moscow, where he also joins the GIRD, which is the civilian rocket organization performing rocket research in the Soviet Union. During 1938, his team makes little progress, and during the Great Purge, he is imprisoned, where he will remain in prison until 1944, when he's released by order by Premier Stalin. Now, what happens is Stalin receives a personal letter from Winston Churchill, uh, which describes a secret rocket base which launches V-2 rockets in Blizna, Poland, that will soon be overtaken by Russian forces. Churchill asked Stalin not to destroy the base and to keep the installation intact until British agents can arrive on scene to extract the technology from the German V-2 rocket. So now Stalin knows there's a V-2 rocket program. He asks for a panel of experts to be assembled, and they determine that their chief rocket expert, Korolev, is in jail. So he's released from prison. He's promoted to the rank of colonel, and he, with another team of military experts, heads to Blizna, Poland, where they extract V-2 rockets and they develop their program for the Soviet Union. Now, much like the U.S. Operation Paperclip, where 117 engineers are sent to the U.S. to work on rocket research, the Russian program assembles over 200 engineers that were left in Germany, and they get around 30 V-2 rockets at Blizna, Poland, and also when they take possession of middle work from the United States later in 1945, there'll be some hardware left over there as well. So they have enough V2s to make 30 rockets, where the United States transports around 80 back to the United States for testing. So now we have the Russian program, which starts working on V2 technology, which is also similar to the US program working on V2 technology. And I think the thing to note here is how these two gentlemen were influenced by the three gentlemen above. So if we really look at that, it's going to be this Tsiolkovsky, Goddard, Oberth, and they really influenced both of these gentlemen. So the US program leads directly from the V2 to the Redstone, and this is a single stage rocket. And please note, this rocket cannot reach parking orbit, but it did pass the Kármán line, so it is able to boost humans to above 100 kilometers in altitude, but it cannot do a stable parking orbit. So really, to get to a parking orbit where we could do multiple orbits around the planet for human space flight, we're going to need to transition to these multi-stage rockets. And this is where the Russians come in. So Korolev skips the whole single stage development activity and goes directly to multi-stage. And this is really kind of a tribute to the gentleman before. As we note, Goddard had the original patent for multi-stage rockets. So Korolev and von Braun are very influenced by the teachings of these three men, Tsiolkovsky, Goddard, and Oberth. And if you want to read more on that, there's a great paper by Michael Neufeld. He's the curator at the National Air and Space Museum in Washington, D.C., and it really explains kind of the rise of Tsiolkovsky, Goddard, Oberth, and the interpretation of and its current validity in today's aerospace community. The Mercury Redstone rocket was used to gather crucial R&D data for the American space program, with the Mercury capsule sitting on top of the Redstone rocket. Now, in this configuration, the capsule would hold a single human being, and the Redstone rocket is based on the German V2 design. Now, the major departure from the original V2 design is that while the tanks are in the same location, so the alcohol tank is on top of the liquid oxygen tank in both the V2 and the Redstone design has incorporated what's called integrated tanks. So rather than putting a fuel tank inside a rocket fuselage, as was done with the V2, in the case of the Redstone, the rocket wall of the tank is the structural member of the fuselage. So this helps save weight, and with the same engine and gas generator configuration, because we're saving weight, it allows a higher altitudes to be reached with this particular rocket configuration. The German V2 rocket payload is essentially a warhead comprised of 1,000 kilograms of explosive. If we compare that to the payload of the Mercury Redstone, which is essentially the Mercury capsule plus this escape rocket tower, we see that it's almost 2x or 1,830 kilograms. The first American will be launched on a Mercury Redstone rocket on May 5th, 1961. So Alan Shepard is inside the Mercury capsule, and he's leaving Cape Canaveral Air Force Station on his way to an altitude of 187 kilometers. Now, it's not the first human put into space, it's the first American. Yuri Gagarin will be the first human placed into space several weeks earlier in April aboard a Vostok rocket. Alan Shepard is the first American to be launched into space aboard a Mercury Redstone rocket on May 5th, 1961. If we look at Mr. Shepard's launch in more detail, we know his ascent acceleration was just over 6 Gs, and this is a picture of Mr. Shepard shown inside the capsule. And after his mission duration of 15 minutes and 22 seconds, you can see him being hauled into a helicopter after his mission duration from launch to splashdown. Now, his combustion burn time for the motor was 142 seconds, and he reached a maximum altitude of 187.5 kilometers at apogee. Now, the next person to go into space was Gus Grissom. His ascent acceleration was just over 6 Gs, and we see a picture of Mr. Grissom here next to a Redstone rocket in the factory. And we should also note that the first primate that was launched into space from the American program was a chimpanzee named Ham. Now, Ham is named by acronym after where he was trained at Holloman Air Force Base Medical Center, or HAM. And poor Ham experienced 14 Gs during launch ascent. It appears the throttle was stuck wide open, and the vehicle kept burning until it ran out of fuel. So very important information retrieved during Ham's mission. He was retrieved aboard a Navy vessel, and the officers noted that he took an apple from one of the officers and ate it immediately. He was in good health, and he was retired to a zoo after this and never flew again, and lived a long life. I think he lived another 20 years after this in captivity in the zoo. But very important information retrieved prior to putting human beings on board, and both Mr. Shepard and Mr. Grissom owe Ham a gratitude for not having to experience that 14G launch acceleration. Let's take a more in-depth look at Alan Shepard's mission. So we note that his ascent acceleration was just over 6 Gs, and if we look at his mission profile, we note that it's in time, minutes, and seconds of duration, and this is going to be 15 minutes and 22 seconds from launch to splashdown. So the next thing we want to look at is his lateral distance. It's around 487 kilometers away from the Cape Canaveral launch tower. We described his maximum altitude at 187.5 kilometers in the previous slide, but the thing we're really interested in is his max speed. So he reached a maximum speed of 2.3 kilometers per second, or 5,300 miles per hour. So this was with a burn time of 2 minutes and 22 seconds. If we put that into perspective of the whole mission for the parabolic flight, we can see that's only this small period right here. This is the combustion time for the rocket motor. So if we look at our previous slides on the International Space Station parking orbit velocity, we note that we need a velocity of around 7.668 kilometers per second to reach that 404 kilometer altitude. Now, if we compare that to what we had for the Mercury Redstone rocket, we note that it's 3.33x too slow a velocity to sustain a typical International Space Station parking orbit altitude. So we're going to need another technique to get to orbit to be able to reach stable parking orbits and higher altitudes. All rockets used to launch humans into parking orbits from 1961 through 2020 are all multi-stage in nature. Now, if we compare the original Mercury Redstone rocket, it saw a G load of around 6 Gs during ascent for the astronauts. If we look at the American programs from Mercury Atlas and Gemini Titan, we note that they saw around 7 Gs during launch. Now, this was dropped on purpose for the Apollo program. For the Saturn 1B and the Saturn V, it was dropped down to 4 Gs. And for the Space Shuttle, at an even lower 3 Gs. Now, this is by design. Now, let's look at these rockets from the Russian and American programs. These first three, the Vostok, the Voskhod, and the Soyuz, are all ICBMs that were converted for astronauts. Additionally, the Redstone, the Atlas, and the Titan were also ICBMs that were converted for human transport. So really the first two sets of rockets that were designed especially for human transport were the Apollo Saturn 1B and Saturn 5 and the Space Shuttle. Astronaut transport to the International Space Station from 2011 through 2019 was accomplished using the Russian Soyuz rocket. This was consequently designed by Sergei Korolev before he passed away in 1966 and has been in service since 1967 with an amazing safety record. The Space Shuttle program was in service from 1981 through 2011, and when it shut down, it required us to move over to that Soyuz rocket in order to put Americans at this International Space Station. Now, 33 missions were used over the lifetime of the Space Shuttle to lift ISS components into parking orbit and help assemble the different components of the International Space Station. Now, two methods are viable for American astronauts to reach the International Space Station in mid-2020 and beyond. The first uses the United Launch Alliance Atlas V with a Boeing Crew Starliner on top of that, and the second will use a SpaceX Falcon 9 with their Dragon capsule. Now, beyond that, when we really set our sights on the Moon and Mars, this is really where the Space Launch System Block 1 and Block 1B will service Moon and Mars missions in the future. The Atlas rocket used to reach stable parking orbits was a modified intercontinental ballistic missile, or ICBM. The warhead payload was replaced with the Mercury capsule, and this rocket is comprised of two stages. The first stage has two nozzles that are optimized for low altitude operation at 1 atmosphere near sea level. The second stage has a single nozzle that's optimized for high altitude operation near vacuum pressure. So if we look at our velocity required for an International Space Station parking orbit velocity, we note that that's near 7.668 kilometers per second, and we are able to reach and exceed that speed with the Mercury Atlas configuration at 7.832 kilometers per second. And in fact, this is 3x greater with respect to a velocity increase as compared to the single stage Mercury Redstone. Mercury Atlas G loads were measured per launch data on November 5th, 1962, as shown below. For the first stage, we note that the acceleration data will start at 1 G at ignition and quickly ramp up to about 1.5 Gs in 1 second. Now, the acceleration will slowly climb until it gets just below 7 Gs at that first stage separation. Now, when we get to the second stage, we note that the acceleration will again climb from around 1 G to just below 8 Gs at the end of the second stage burn, or that sustainer engine cutoff, SECO, point where the engine is extinguished. The Mercury Atlas program leads NASA to evaluate G loads pertaining to human spaceflight. If we look at the vertical axis, it's acceleration in Gs experienced by the astronauts, and the horizontal axis is time and duration. Now, if we look at the curve at right, we note that this represents the acceleration curve for fuel as it's combusted in the rocket engine. So the entire mission of combustion was 5 minutes and 10 seconds. This is the burn time for the motor. And even though the mission is 3 hours, 20 minutes and 59 seconds, this will be the time during ascent that there is acceleration due to that thrust from the engine. So for the most part, if we use a 2-minute to 10-minute window, we can cover most human spaceflight. As an example, the space shuttle was 8.5 minutes on average to get from launch pad to orbit. So next, we would actually look at the change from ignition to 1.5 Gs in less than 1 second, and then that slow climb to near 7 Gs for the first stage, and then 1 G again with that slow climb up to near 8 Gs for the second stage. So if we were to plot that near 8 G load that the astronauts see for the second stage, we note that we've transitioned into this gray speculative area for the transverse mode. And this yellow area is what we're interested in. Now, the orientation for the astronauts in this case would be this transverse position or supine, and the load from acceleration is going to be along the vertical axis. So they're going to feel like they're getting much heavier in a 1G load as they take off from the launch pad. And that acceleration, again, is along the major axis of the vehicle. Of most concern is the change in acceleration with respect to time. So it's that first derivative of acceleration with respect to time. So if we look at our first event, this would occur right at ignition, and we would take this 1.5 Gs minus 1 Gs divided by that 1 second transition and end up with a positive 0.5 G per second transition for the astronauts at ignition. Then we get a slow change in acceleration over time, so very gradual, up to around 7 Gs. Now the next event, this is pretty high, so it's going to be this 1 G minus 7 Gs divided by 1 second, or about a negative 6 G per second transition. This would have been quite unpleasant for the astronauts as they transition from that booster engine cutoff to the second stage or sustainer engine. So the third transition would even be worse for the Mercury astronauts, where they transition from near 8 Gs to 0 in a very short time frame. So this would be approximated by this 0 minus 8 Gs divided by 1 second with a peak of minus 8. And this is a very rough approximation. It just gives you a feel, with an estimation of 1 second per duration, that these G levels are quite high. And compared to that of ignition, the negative accelerations are much larger than the positive acceleration at ignition or launch. G loads for the escape system on Mercury, Gemini, and Apollo programs is shown here. Similar to the previous slide, we see acceleration in G's on the vertical axis with time and duration on the horizontal axis. Now, the addition of the rate of change of acceleration with respect to time is shown here with a slope, and this represents 1500 Gs per second. So we note that this will be the criteria, this change in acceleration with respect to time, for the limits of human tolerance to linear acceleration. The escape system for both the Mercury and Apollo programs is shown here. It consists of a solid rocket booster connected to the top of the crew module or capsule using a launch escape system tower. Now, this solid rocket booster would ignite and pull the crew module away from the rocket should an event occur during launch that would be dangerous to the astronauts. Now, this is known as a tractor system when it pulls the capsule away from the vehicle with the rocket on top of the crew module or capsule. Now, if we look at left, we see our acceleration in Gs versus duration in seconds. Probably an easier way to represent that is with a color code. And if we look at the red, this is the major axis that we're going to want to expose the astronauts to Gs. So this would be along the major axis of the vehicle. And you could see that this is, from a human tolerance standpoint, the highest level that humans can endure without physical damage or harm. Transverse acceleration is shown here in red, and this represents the highest tolerance for acceleration for a human being regarding human spaceflight. Now, this would be oriented using this anthropomorphic astronaut from front to back, and we note that the acceleration for the Mercury capsule would be along this major axis. So that G load during launch ascent would actually point in this direction toward the astronaut. Similarly, during launch for the Gemini capsule, it would point in this direction. And if we see the Apollo capsule also along this major axis as well. So the astronauts are oriented purposefully in the axis at which human beings tolerate that change in acceleration with respect to time, with the highest level as shown here in red. The Saturn V transverse launch acceleration can be approximated by looking at the initial 1 second of acceleration data. If we approximate that, we would have 1.2 Gs minus 1 over 1 second, or approximately 0.2 Gs per second. It should be noted that for the Saturn V, the largest acceleration along the transverse axis with respect to launch is during that stage 1C, stage 2 separation event that's shown here. Now, if we approximate that deceleration, we would have 0.5 Gs minus 4 Gs over 1 second, or negative 3.5 Gs per second. This would be highly unpleasant for the Apollo astronauts as well, and represents the largest transition in acceleration per second, or that change in acceleration with respect to time for the Apollo astronauts. Transverse acceleration data for the space shuttle is shown here. We note we have that separation event for the solid rocket boosters that occurs around 123 seconds. And we can consider that to be a first stage for the solid rocket motor plus liquid rocket engine. And the second stage would represent the liquid rocket engines only. So now, if we look at that first transition event from ignition through 1 second, we would approximate that using 1.6 Gs minus 1 G over 1 second, or around 0.6 Gs per second of transverse acceleration. So if we were to look at the next event and calculate that deceleration through the tail off of the thrust of the solid rocket boosters, as shown here, through booster separation, we see that the G level is quite low. So it's negative 0.09 Gs per second is approximated. And it's really because that tail off and thrust has distributed that change in acceleration or deceleration over tens of seconds. In fact, in this case, it's around 16 seconds. So that represents a significant drop in the acceleration transverse change with respect to time, and a much higher comfort level for the space shuttle astronauts. So in closing, we look at the rate of change when the liquid rocket engines or RS-25s are cut off, and that's going to be approximately 2.8 Gs per second. So this would represent the highest value of deceleration for the space shuttle launch event, but again, much smaller than that 3.5 Gs per second deceleration rate experienced by the Apollo 11 astronauts between that stage 1C and stage 2 separation event. The thrust-to-weight ratio for a rocket must be greater than 1 to satisfy a vertical liftoff condition. We note that thrust for a rocket is the mass flow rate times the exhaust exit velocity plus the dynamic exhaust exit pressure minus the static ambient pressure multiplied times the area of the de Laval nozzle exit plane. Now, the weight of the rocket is the structural mass of the rocket plus the propellant carried by the rocket in units of kilograms times 1g. And we also note that newtons is kilograms times meters per second square. So these are in the same units of force. Now, if we look at the thrust-to-weight ratio for the space shuttle, we note it's at 1.6, and that's 1.6 Gs after 1 second of ignition for that solid rocket booster. Compared to other rockets, the Redstone, Atlas, Titan, Saturn V, we note that the space shuttle is much higher, and that's really a function of those solid rocket boosters providing significant thrust off the pad. We note that for liquid rocket engines, the acceleration is typically quite slow, and although high acceleration can be achieved, it's not as rapid as can be experienced with a solid rocket booster. Now, for the rest of our table at left, this thrust-to-weight ratio, we note that for airplanes, unless the thrust-to-weight ratio is greater than 1, it cannot sustain vertical flight. So for these other vehicles, they're winged, they use lift, so they can fly, but they can't take off vertically. This would be the point at which the vehicle could hover, but not move forward. And for values greater than 1, these planes can actually fly vertically. The effective exhaust velocity versus thrust-to-vehicle rate ratio is shown below in figure 2-4 as extracted from rocket propulsion elements. We note that we need a thrust-to-weight ratio of greater than 1 to sustain vertical flight for a rocket, and this limits us to propellants on this portion of the table. Using a target delta V of 7.668 kilometers per second to reach the International Space Station, we have a limit of 2.6 kilometers per second to 3.9 kilometers per second for our exhaust exit velocity. This really will limit us to liquid and solid chemical propellants in the table, as shown above. If you're interested in additional information on liquid propellants in this portion of the table, the book Ignition and Informal History of Liquid Rocket Propellants by John D. Clark is quite informative. Now, if you take this portion of the vertical axis, which is the effective exhaust velocity, and divide by 1g, 9.807 meters per second square, you'll be left with ISP in seconds. So what I do is divide by 10. So for an electromagnetic Hall thruster, we would have 2,000 seconds of ISP. While this is quite impressive and works great for vehicles that are already in a zero-G environment, this would not be effective from a ground standpoint to try to get a vehicle into space. So again, great thruster while you're in space, an amazing exhaust exit velocity and ISP, but from sea level to orbit, this is not a useful form of thrust. Recall that the Tsiolkovsky rocket equation, as shown previously in video 2 on slide 53, can be solved using a Newton's second law of motion, as shown here. Now, what's been done is we've accounted for the total mass of the rocket, which is the structural mass of the rocket plus mass of the propellant before ignition, and just the structural mass of the rocket after all the propellant has been expelled. Now, this ends up with a compact term when we solve for the delta V for the vehicle, as shown here. In conclusion, we've used Newton's three laws of motion to describe rocket thrust. In particular, we've started with Newton's second law of motion, and we've distributed it out and also subtracted the force due to ambient pressure and the area of the exit plane de Laval nozzle. Now, when we solve through, we end up with a compact term for force, as shown here, that describes the force in newtons for a de Laval nozzle in terms of the mass flow rate, m dot, times the exhaust exit velocity, plus the dynamic pressure minus the static ambient pressure, times the area of the de Laval nozzle exit plane. As an additional step, we've distributed the force of thrust in terms of the dynamic exhaust exit pressure and static ambient pressure, and also in terms of the exhaust exit velocity. This concludes derivation of the thrust equation using Newton's second law of motion. We'll conclude this video series with a brief description of Einstein's special and general relativity as they pertain to the enhancement of the interpretation of modern-day Newtonian gravity. First, we start with Einstein's special relativity in 1905, which states the laws of physics are invariant in all non-accelerating inertial systems, and that the speed of light traveling in a vacuum is the same for all observers, regardless of the motion of the light source. It also gives us the famous equation E equals mc squared. Now, in 1915, Einstein publishes general relativity, which combines special relativity with Newton's law of universal gravitation to provide a unified description of gravity as a geometric property of space and time, or space-time. Now, this can be interpreted as two massive objects, such as black holes, will be in a locked orbit around each other, causing ripples in space-time, which could be measured as gravitational waves. And this was accurately predicted by Einstein's general relativity. Now, if we note that we need this Einstein special and general relativity to be applied to gravity in order to work with things like global positioning and communication satellites in their higher velocities and lower gravity orbits, such as geosynchronous locations. When it comes to rocket or chemical propelled rockets, this propulsion is very slow, and that Newtonian mechanics and gravity accurately describe the chemical propellant rocket propulsion due to the low magnitudes of gravitational field and the low mass particle velocities with respect to light speed. Our modern day interpretation of gravity is a function of the work of Einstein plus Newton, not Einstein versus Newton as depicted here. So please note that modern day gravity is a function of general relativity coupled with the work of Newton in Newtonian gravity. So if you're interested in additional information on gravity, a great book is called On Gravity by the author A.Z. Please accept a sincere thank you for your time and consideration regarding our entire presentation team. If you have any questions or feedback on any of the 4 videos shown here, please direct them to my email to either Northrop Grumman or Stanford University at your convenience. And again, thank you.